Now let's start the recording.
Record.
And can you hear my voice clearly?
Yeah.
Okay, that's pretty good. Now, as I've said, we have plenty of things to talk about today, so let's rush because this is, I may say, the most important lecture for C programming because it is essential that you understand how pointers and arrays and memory addressing work. Otherwise, it would just be a simple plain language that you cannot do anything in, and it would just be for displaying it over your CV that I know how to program in C, but in fact you don't know nothing. Okay, the most fundamental operations that comes to your mind when you think about programming is done with pointers in C. So we're going to have to paying attention to whatever is being talked about here. I'm going to be reading them out loud and then explaining them because, as I said, I don't want to miss any words in these sentences because they're all pretty important. So I want you to pay attention to all of these. An array, again, I'm reminding this is the lecture part 2 for arrays and pointers. An array is just a pointer to the beginning element of a sequence of variables, which is the definition of the array, as you know, sequence of variables. However, compiler pays attention to how indexing is done in the code, so no buffer overflow occurs. Okay, so what this means is that buffer overflow, as we've stated in the previous lectures, is the error that happens when you try to access the rightmost side of an array, which is out of the boundary of the array. So it's basically like you can think of the memory as a sequence of bytes. Let's say all of these zeros represent a byte, and your array just stops here. As you said, these arrays, whether initialized or uninitialized, are stored in the BSS section, or if you allocated them with malloc, they're stored in the heap section, and if they are local variables, they're stored in the stack. So they are laid out in memory in some sort of section, but they have an ending, of course, because they're arrays and they have indexes and they have a last index. And when you try to access the element after that last index, which is physically available, if the array is not located at the end of the RAM, it is physically available in the RAM, and you try to access that byte, which is after the array, you're accessing somewhere that you must be accessing because it's out of the boundaries of array. This error may not be familiar to you from other languages because they do protect their arrays to prevent buffer overflows, but C does not do that to provide you with more freedom, but you have to pay attention as a programmer, as we are going to be talking about in the secure programming lecture. You have to pay attention to these to write secure code so that your code doesn't override somewhere that it mustn't be doing. The famous buffer overflow and buffer overflow. I forgot the word. Buffer overflow exploit, exploit is caused by an input being copied from a text box to an array without being checked for its length. So this is a pretty important thing in secure programming. The compiler pays attention to how indexing is done so that no buffer overflow occurs. However, if the space of your array, if the length of your array is dependent upon what happens in the runtime, like for example, it's dependent upon a variable, you are not going to be, the compiler is not going to be able to check that. So you have to check that yourself. And another difference between arrays and pointers is that whether they're local, uninitialized, initialized, they're allocated from the heap, they're all variables, but arrays are a sequence of variables and pointers is just a variable. Pointer is just a variable, so it is 1 byte or how many bytes, it depending upon the type of the pointer. Like for example, a char, actually not depending on the type of the pointer because memory addresses are all represented in the same data type, in the same length of bytes. So it occupies that space of RAM in the RAM only for every pointer type and nothing more. Whereas an array occupies a space that is occupied by a sequence of variables. So when you define an array, the space that is required to store that sequence of variables is actually allocated in the memory, whereas in a pointer, only one variable sized block of memory is allocated. So when you define a pointer, you actually don't have anything inside of it, okay? Of course, it's uninitialized to 0. Therefore, all the elements of arrays as well. But the elements of the array actually are data, while the data inside the pointer would be just null because it's equal to 0, and you have to first assign it to something, some space in the RAM so that you can use it, okay? And the similarities in between them, as we talked about in the previous lectures, are beautifully demonstrated by the fact that array indexing in C, like for example, when you do this indexing, C automatically converts this to this, because we have pointer arithmetic, which says that constant values can be incremented and decremented from pointers, so that amount of spaces of that data type which the pointer addresses to are incremented and decremented from that pointer. So the left side is equal to the right side, and the compiler automatically converts the left side to the right side before compiling the code. This is a pretty good representation, demonstration of the similarity between arrays and pointers. Actually, they're the same, as we've said, almost. All values are initialized to 0, as we've said. All of the variables, if you haven't initialized them, if you just went on with chart C, are initialized to 0. So a pointer is initialized to 0, and an array, all of the elements inside of this array are initialized to 0 as well. So by default, they are 0. But again, I repeat, you can access the values inside of an array once you declare it, even if it is not initialized by you, because there are physical values inside of the RAM that are pointed to by the array. But in the case of a pointer, you tend to think that some space is allocated for that pointer so that it can address to an array, but really no. In reality, it is just 0, which is the null pointer, which doesn't, address to anything, and it's so you have to first say to your C program that, hey, this pointer actually equals to this array's address, so that you can then try to manipulate some values inside of the pointer. And I say inside of the pointer, but really do not think of the pointers as arrays, although they're pretty similar. They're pretty different things. And when you have to use arrays, not pointers. And well, you can say while taking the argument list as double pointer argv, when declaring a function, specifying the type of its argument, instead of writing this, you can write the one above. It is completely valid. But inside of your code, outside of that, when you have to use arrays, use arrays almost everywhere. You're going to be learning this by experience, the differentiating between them, but do not use pointers for the most part, because they are pointers. They are designed to point to something. They're not designed to be arrays, although they're similar, because their inner workings are pretty similar, not because they're designed for the same thing, okay? Moving on. So beware that the pointer is initialized to 0, which is a null pointer, and when you try to dereference it, which means try to access the value stored inside of the address that is pointed to by the pointer, you get an invalid value, an error, a segmentation error, because you're trying to access somewhere you don't have to. This is a segmentation error, and you may remember from the lecture about memory segmentation that segments in the memory are different parts of the program where data or code is stored. So a segmentation error is just saying that you're trying to access some segment that you mustn't be accessing. And null pointer, which is 0, is always allocated to something else, and you mustn't be accessing that. So you have to first assign something to that pointer, okay? And this would also not work, because remember that this C pointer right now has the null pointer in it, which is 0. So it is pointing to the address 0, and now you're trying to, change the value inside the address 0 to 10. which is again an invalid operation. So don't do that, okay? Don't do that. And yeah, I think this demonstrates the difference, actually the inner working mechanism of initialization and how pointers and arrays work pretty well. So use arrays when you have to use arrays. Initializing a pointer does not initialize the value it points to, because initializing is to 0, which would make it null. Thus, you either need to give the address of a variable to that pointer, or malloc. The same thing we've just said before, but instead of that, it says, like, for example, you have char pointer C, and you have a value, you have a char value, which is C, and you can do this. But instead of that, you can also do this. Okay, the size of operator, you may remember from what happened, you may remember from the previous lecture. You can also borrow space from the heap via the malloc function, which is part of the standard library, which would allocate some space for you in the heap and return the pointer to that section so that you can assign it to a pointer. By the way, this is returning a void pointer, so you have to cast that into a char pointer by that syntax, but it would work. There's no problem with anything. And this is actually the concept behind it. Malloc is just a way of, as we've said in the previous lectures, getting new space from the operating system, because you know, it is mandatory sometimes. Because you sometimes cannot know how much the array has to be, so you have to decide that on runtime, or you actually, I cannot exemplify that. You're going to be seeing that by your experience. Uninitialized and initialized arrays values are all 0. Thus, you can do anything with that, but in order to change the data inside an array, you have to pass its beginning index to the function, because pointer arithmetic is the same as array indexing. However, you need to make sure you don't exceed in your indexing inside the function to not buffer overflow. What this is saying is that actually in C, as you know, in order to modify the actual value of a variable inside of a function that is outside of the function that we're dealing with right now. Like, for example, I'm in the main function right now, and I want to modify the value of the input with another function. So I have to pass the pointer of that input to the function so that it would modify the value that is inside of this address, which is pointed to by that pointer input. Okay, this is pretty important for you to understand. Just passing on the variable would not change it, as we've talked about in the scoping lecture. It has to be passed as a pointer, and this would not change the pointer as well, because pointer is another variable. It would change the data stored inside the address pointed to by that pointer. Okay, it's a pretty important concept. And you have to understand this. And what this thing that I've just read says is that an array is just a pointer, as we've said. So in order to modify an array, just passing on its name, like for example, we have an char array here that is the size of 10, and you can pass this to a function, and this would just work fine as this would do. But beware that you're not exceeding the size of the size of the array when doing something inside of that function. So maybe you can take the parameter of the size of that array. Maybe you can compute the size of that array inside of this function, but you have to do that in order to avoid buffer overflow. And actually, determining the size of an array is just as easy as this. See, as you can infer, this gives the space occupied by the array divided by the space occupied by its single element. Instead of char, you may do this as well for it to be more convenient, and this would all work just fine. Remember, parameters to functions are local. Change that. parameters of functions are local copies inside of that function, inside of that function scope. And changes were made to that pointer, its original one is not affected. But since that pointer points to something, the value in address that is pointed to by that pointer is changed. If you want to change a pointer, define a pointer to it, which is this syntax over here. You can define a pointer to a pointer to a pointer to a pointer and infinitely many times, as long as your RAM allows it. The yesterday's example of just this declaring a struct pointer and not being able to assign some struct. Let me show you this with multiple windows. We have this stack structure, right? We have this, actually it is in the lecture.h file, but we have, as you can remember, this stack structure that was defined like so. It was stack 1024 and a stack pointer was present as well. Maybe we can do this unsigned even, right? Because stack pointer cannot be 0. Maybe unsigned T. No, so maybe this, no, okay, whatever. And this is the struct named stack. Okay, now it's giving errors because the file here defines a different stack. But just to give, just for the demonstration purposes, we're not gonna be holding that on there. So yesterday we tried to do something like this. Okay, we tried to do some malloc thing over here, which was my mistake really. And we tried to initialize that to a structure. Now, the first mistake here is that I'm trying to, this syntax here is a syntax for structure, and by the order the elements are defined inside the struct definition, these the values you give inside of these parentheses are assigned to these elements. So like if this was really a valid definition, the stack for this stack variable would be this, and the stack pointer would be 0. Okay, but now this is an invalid because what you're doing here is assigning to a pointer to a stack a structure, but this is a pointer, so no structure can be assigned to that. It has to be a pointer that is assigned to that variable. The first mistake was that, and the second mistake we did was, okay, let's just define this. And then let's like do this. Why not? Well, the problem here is the thing we've been talking about from the beginning of this lecture is that this stack pointer holds right now the value of 0 inside of it, which is the null pointer. And since it points to the 0th address, which is invalid to access, we cannot say to the compiler to do something there. Okay, it is invalid because there's nothing there. And also, even if this pointed to a valid address, this will still be invalid because no allocation for these were not done. You get what I'm saying? No allocation for these were not done. So we would have to first allocate some space by this exact syntax we're using here. Like we're defining the function, we're defining the pointer, and then inside of this, we're saying that the stack pointer is 0, and what is this? Okay, we're first allocating some space in the memory to hold the data type stack in it, which is done by so, and then we set its stack pointer to 0, and since this now kind of initializes in an uninitialized way the whole structure, now we have an uninitialized stack pointer that is accessible by this syntax, and also uninitialized stack that is accessible by that same original syntax, and they're all zeros because they're uninitialized. Okay, So we had to first allocate some space in the memory to hold the stack, because we did not have anywhere in the RAM that is saying there's a stack type of struct laying here. We did not have any. We created that. We took its pointer with malloc and assigned it to stack, and now we can manipulate it however we want. And this syntax over here, which is creating a space in the RAM for a struct stack, actually creates these these areas in the RAM as well. You may think of it that way, and this would make for you some uninitialized and ready to use variables. And beware also that for the differences between arrays and pointers, I don't have to initialize that stack as I did with the stack pointer. I don't have to allocate any space for that, because since it's an array, C already allocates some space for you, because then why would it be an array, right? The yesterday's example of just declaring a struct pointer and not being able to assign braces to it, or trying to access its elements without creating a structure with malloc, yeah, this was another mistake we made. We did this and we tried to access its stack pointer like so, which is invalid, because as we've said, there is no space in the RAM that is allocated to store some data type of the type struct stack. Okay, so we cannot do that. Continuing its elements without creating a structure with malloc, or a variable whose address is assigned to the pointer. So we might just as well do this. Stack 1 and do some malloc size of char and multiply it with 1024 and then 0 and then braces, and then we could do that. Since these pointers are all variables, there's no invalidity here. Okay, let me actually, this would be invalid because we're trying to assign a pointer to array, so we can just leave it as b. Oh, sorry, I lose the file. All right, so we can just leave it as b, so that it would be uninitialized data inside of this array, but it would be valid because pointers are just variables and you can do anything with them that are being done with pointers, right? With variables, sorry. Its elements without creating a structure with malloc, or a variable whose address is assigned to that pointer. Then the circle continues for pointers inside of this structure as well. So like if we had some pointers inside of this stack, we would have to do the same thing for them as well. A pointer that is uninitialized points to nothing. Understand this. Because a variable this pointer points to does not exist yet. Initialize, this is garbage. When a variable is created, if not initialized, they are defaulted to zeros. The point you declare a pointer, you're defaulting it to 0. Once you create a variable, this pointer points you declared points you to points. And what does it say? Once you create a variable, this pointer points, you declare that variable, thus everything inside of them are initialized to 0. Once you declare the variable with some sort of medium, like with malloc, as seen here, or with just saying its name, once you declare it somehow, even if you do not initialize it, the space in the RAM is created for that variable. Okay, the space in the RAM is allocated, the enough space is set aside, and the computer is informed that some variable of that data type is laying there, so don't allow anything else to access it, and they're all uninitialized to some value. Whatever they are, we don't know, but they're zeros, but there's something laying there. So even if you do not initialize this array, you can access these elements even if they are not uninitialized to zeros. There are some things lying garbage value which were left from the previous state of the RAM that you can access because they are physically allocated. The point you declare a pointer, you're defaulting it to 0. Once you create a variable, this pointer points, you declare that variable, thus everything inside them are initialized to 0. Just think of it this way, and you will apply these to all cases. You cannot address elements of a structure if no structure is yet created, which is just this scenario we have just created. So understand this, and you're going to be just fine programming in C. This is maybe the most important part of the lecture, and let's move on. Because you don't have any kind of protection by the programming language to your indexing of the array, which is just addressing different elements inside of the array with this syntax, of course. You always need to check whether you have exceeded the array size. And because pointers are not arrays, C does not initialize an array of values for them. If you want to use pointers as arrays, that being instead of writing int this syntax, you want to use this syntax, just don't, or malloc, but then don't. But then you would have to keep track of free. You would have to free this. It does not matter in this program because this stack variable is used throughout the whole of the program, and once the program exists, until the program exits, the stack variable is used, so there's no need to free them. But in some scenario where you would not be using some malloced variable until the end of your program, you would have to free it once your job is done with it. And without that, we would have the case what as we call memory leak, which is allocating spaces and spaces and spaces of RAM, and once your job finishes, not deallocating them, so filling RAM unnecessarily and slowing down and maybe crashing your computer. So don't do that. You have to keep track of the free if you're using pointers instead of arrays. When an array name is passed to a function, the function can, at its convenience, believe that it is being handed either an array or a pointer and manipulate it accordingly, like arg, which is what we have just described about this thing. Function arguments can be given if they're representing arrays, of course, as in the pointer syntax or the array syntax. It does not matter. How you handle them and how you initialize your arrays are what matters. The function pointers do not matter. I can just very well do this over here, which would actually be the more correct syntax, but it doesn't matter when declaring the function pointers. But then I would have to say the number of elements inside of the second one. So maybe sometimes this is also convenient. Arithmetic on pointers decrement them by the number of bytes used by data type they point to. Like, for example, if I am incrementing a pointer to integer by 1, by a constant integer value of 1, and let's say the machine I'm doing inside behaves the integer as 4 bytes, the pointer arithmetic would yield the result of the address stored inside of that pointer plus 4 bytes, which is actually which actually would follow that it would just get to the next thing, next integer inside the RAM. Just think of it as well, as so. And we have a const keyword, which is this thing I just want to quickly introduce here. This prevents any modification to that variable later in the program because it's const, which is short for constant. And we're going to be talking more about that in terms of in the space of chars right now. So this is a pretty good answer, actually. Mutable means editable and immutable means uneditable. So you can think of this as not const and this as a const. This syntax, maybe you would need it or not, but C has these weird syntaxes that feel good to be programming in, which you would almost never need. But, we can just read that out and pass on because it's not really that important. But just so you know the distinction. Char asterisk is a mutable pointer to a mutable character or string. Const char asterisk is a mutable pointer to an immutable character string. You cannot change the contents of the locations this pointer points to. Also, compilers are required to give error messages when you try to do so. For some reason, conversion from const char asterisk to char asterisk is deprecated. Yeah, there are weird features in modern C compilers too. The C is standardized by the American National. No, I don't know what NSI stands for, but by this institute, the C is standardized, and the last standard I guess was C11, which is no, last standard was C17. Okay. Oh, we have okay, which is released in 2018. So these guys, release regularly standards for C and sell them for high prices. Char asterisk const is an immutable pointer. It cannot point to any other location, but the contents of location at which it points are mutable. Const char asterisk const is an immutable pointer to an immutable character string. This is a pretty good explanation of this, how this works, and how you can understand a lot about C syntax by that. C has a lot of weird syntax, and actually most of them are pretty useful if you know how to use them. But C is mostly used by systems programmers nowadays, and most of the programmers are not systems programmers because, yeah, whatever. Let's move on. In C, you cannot compare strings because there's no data type called string. You only have char arrays. And can you compare structs? Okay, they do not as well. Do not think of C as a modern programming language because modern programming languages are not programming languages. C was the holy grail. Let's move on with this syntax over here. I'm going to show it in the code section. Why cannot I? Let's the semicolons in. Okay. Why does it give error? Okay. So first, you always and always and always and always have to specify the size of an array in C. So yes, not like Python, you cannot have an array that is customably stretched and unstretched for you by the programming languages, but we have dynamic arrays in C and we're going to be talking about them in this lecture. So you can have infinitely many sized arrays. So you don't have to allocate and allocate and allocate and do some complex stuff with it. So we have to first specify the size, maybe 10, let's say for this example. And now another thing we see here. Anlamadım. Dersi bir oldu. Bir şey mi diyeceksin? Bir şey mi diyeceksin? Ha, eyvallah. Listen to Taylor Swift, the quote of this lecture. Arrays are not assignable unless you're doing it when you're declaring. Actually, this is called assigning. Unless you're doing this, you cannot assign to arrays, and it's is a buffer overflow we're doing here because C is allocating 10 char spaces for that variable, and now we're trying to put more of that, but whatever. You cannot assign to arrays like demonstrated in this example. Okay, you cannot do that. And you can only initialize them, but once you want to change their values after initializing them, you would have to manually do this in a loop or something, but you would have to index their elements one by one. So keep that in mind. And a pretty good excerpt from the C programming language book written by Dennis Ritchie and Brian, what is his name? Brian Kernighan, who are pretty good computer scientists, They were the fathers of computers. And then they were not childs of computers because they were abandoned for some JavaScript bullshit. But let's remember these beautiful men once more in our lifetimes so that to honor their memories in their contributions to our modern day technologies, that these men created Unix and the C programming language in a modular, smart, scientifically and technologically and philosophically and artfully masterful and respectful way for just to ease their own jobs, daily jobs inside computers, at the end, changing the whole world by integrating computers into everyone's homes, and finally leading to TikTok, which is the most fortunate, unfortunate, one of the most unfortunate events that ever happened to humanity in the last 50 years. But these were good men. I say were, but he's still alive, I guess, Ken Thompson. He was playing some space shuttle game in his computer in Bell Labs, and I guess he wanted to, make it more mobile or more easy to access. And he said, "Well, I'm gonna develop an operating system for that. It's pretty complicated otherwise." And he developed the whole damn Unix by just as a hobby. And if not, Dennis Ritchie came over. He was more of a social guy, at least compared to him. He would just keep the operating system to himself and would not offer it to public use because he was too autistic to do that. And this guy, I guess, has a Trinks medal, and you can view his page at Bell Labs. Okay, this is the Bell Labs page for Dennis Ritchie. He's a pretty good guy. Wish I met him, but I did not. Let's move on. Excerpt from the C programming language, which is the Bible of programming. A, which in this case is this, which in this case is this variable, is an array, just big enough to hold the sequence of characters and null that initializes it. Individual characters within the array may be changed, but A will always refer to the same storage. On the other hand, B is a pointer, initialized to point to a string constant. The pointer may subsequently be modified to point somewhere else, but the result is undefined if you try to modify the string contents. Because, no, in this case, of course, because this is a string literal over here, you cannot modify its contents like doing this kind of thing, but like so. But you would be able to do that had you not, made this a string constant, and instead made this something like an array of characters, actually, like this. But of course, we cannot assign this to a pointer because this is an array and this is a pointer. So we have to do this instead. And then the first element of A, which is D, would be C. And remember that even if we're putting 3 characters inside of A, the other 7 spots are still allocated for A and cannot be modified by another variable. They're initialized or uninitialized. We don't concern ourselves with that. They're not initialized, by the way, because we didn't give them any values at the initial stage of declaration. That's where the word initialization comes from. But there are spaces there. They're allocated. So there is now 10 less charge spaces available in your RAM to be used by your program. Let's move on. Arrays are not initialized. By the way, I have to mention this as well. Now, let's say you put in, this is pretty much. 1, 2, 3, 4, 5. Yeah, let's say you put that in, and you would remember that the last character of a string has to be this. In string literals, C actually puts that for you at the end of the memory and increases that 5 to 6 so that you wouldn't have to concern yourselves with that. And what if you initialize with this syntax or this syntax an array, you don't have to give it size because C would automatically allocate the number of spaces required only to keep your initialization and nothing more and nothing more and nothing less. Okay, so keep that in mind as well. Remember, observe that this is not giving any errors. Arrays are not assignable, but at initialization can be given values with either codes, if it's a string, if it's a char array. By the way, we call these string literals, or braces. If you do not have an initializer, you have to specify size, and C will automatically insert null character at the end of string literals. You can modify elements one by one. After a function exits, okay. This is also a pretty important concept. We talked about memory leaks, and you have to free your allocated spaces. This is just a reminder that once a function exits, the memory allocated through malloc by that function is not freed. You have to free that before exiting that function. This is not the case for the main function because once the main function, since the main function is the main program, and once it exits, the operating system shuts down the process, the program completely. So actually, operating system deletes the whole process and its data and its allocated data from the RAM. Not because the process had freed it, but because operating system completely deleted that process and process had no control over that. Okay, let's move on. But of course, an array would be gone because it's just a local variable. The pointer to that malloc thing would also be gone because it's also a local variable, but the allocated space would still be seen as allocated, although you cannot access it because you don't have the pointer anymore. You don't have the pointer anymore. Okay, you may get core dumped errors sometimes because that is the error that that is given out when you try to access a segment of memory that you mustn't be accessing. Like for example, you are trying to dereference a null pointer, or you're trying to, mostly for when you're trying to, access a null pointer, basically. So don't be confused when you see these expression come up, core dumped error. Stack-based memory allocator, and let's program this. We have a programming task right now to practice what we have done here. And then we have these things. I guess we can work all of these out in an hour, so I'm going to do that. A stack-based memory allocator. Let's open a new file. alloc.h, let's call it, and include that as well in our file because this is different from the one. This file is for purposes other than the purposes of this file over here. So we have to open a new file so that to make our thing modular. And why cannot you find that? Didn't I write this? Let's save this as well. Okay, it's gone. Now, a stack-based memory allocator is just going to be a pretty primitive and unusable, but for our cases usable implementation of a memory allocation, which would work as creating an array, and then it would not even be a dynamic array. So we won't have the number of spaces RAM provides to us, but only the size of the array to us, and it would allocate some part of the memory and yield the pointer to the function trying to allocate that, and then as we said, it is stack based, so you cannot free the one that is last allocated. You cannot free one of them before allocating the one at the top, which is allocated after the one you're trying to deallocate. And pretty much that's basically it. So let's start. We have the buffer, which is buff size long. We're going to define that as well to be, let's say, what is 2 to the power of 20. Let's say this is our buffer size. Why didn't you copy that? Okay, 1,048,576. I don't know why I read that out loud. I'm just gonna do this. Okay. And then at the end of the file, we have to undefine it because other files may have the same defined variable, although it would not be advised. Other files may declare the same macro as the same name with it for different or similar purposes and may overwrite that, so we don't have to want to concern ourselves with. You may think of this as the word static here we're using here to make them inaccessible from files other than that file, so that to not confuse them, and for not to allow other files to modify these contents, so that these contents are only managed by the functions inside of here, so that the mechanism is not broken. Of course, we have to specify its data type, which in this case, let's say it's char. And let's just int allocate and int size. Let's say int size. And we're not going to be concerning ourselves with different sizes of different data types and bytes. We're not going to be concerning ourselves with any of that. We're just going to be returning a pointer to that section. Okay, so let's think. Maybe we want to have a pointer as well. Okay, static int stack pointer. Let's initialize that to 0. And then if we have enough space, if let's say buff size minus stack pointer bigger or equal to size, because let's say stack pointer is 0, we have buff size available. And let's return the stack pointer here, not the stack pointer, but buffer stack pointer address as the syntax goes. And let's increment the stack pointer by size, since that space is now allocated. And whatever the program allocating these does over there, we're not concerning ourselves with it. We're just giving them space, okay? And let's say they did request 1 space, and the stack pointer would be 1. And stack pointer would be 1. And the next time there will be buff size minus 1 available space, and the stack pointer would be at the top, would be further than the allocated space, so nothing would override that. Okay, there's a little mistake over here. Let's create that variable. Res is equal to buffer stack pointer, because we're first incrementing the value of the stack pointer, and then we're trying to return something with it, which would of course, why did I delete that? Which would of course return something invalid. And if this if gives a 0 result, if it gives a false result, then we're just going to return a null pointer to indicate that the allocation is not successful. Okay. Let's do this, right? This is the most modular and simplest way of doing this. Yes, this is pretty cool. Do I have to include the standard library to use this? null pointer. Yeah, I have to. Okay, but this is still more modular. Let's move on and let's say deallocate, and this would just return whether the process has been successful or not. Okay, deallocate, and let's take the pointer to where we allocate memory. And let's say if pointer equals to buffer stack pointer minus oh bir dakika lan. Bitmedi. Ya anlamıyorum Mikail. Gel gel kamerada gözükmüş şey olmaz. El salla çocuklar.
İyi dersler.
Bu da Mikail abiniz. Kendisinin ismi biraz şüpheli. Derin devlettir bu adam.
Can Dündar kim ya? Kim oluyor?
Can Dündar.
Ya
Şey değil mi lan? Mikail'in akrabası değil mi o?
evet öyleymiş. Ya boş yapmayın ya.
Bir dakika Can Dündar şey değil miydi şu Halk TV'de çıkıp
Ay.
oğlum bu kaydı YouTube'a atacağım. Gerçi 3 kişi izliyordu neyse.
Sen çocuklara bir de sonra bir daha devam edecek. Dur şuna şeyle kalmış.
Teneffüs verdik belki.
Oğlum adam öğretmedi. Sen bir şey mi yapıyorsun? Can Dündar kızı istiyorum.
Oğlum Uğur Dündar değil mi o?
Yurt dışında Can Dündar.
Can Dündar senin abin mi? İlhan Dündar mıydı senin abin o?
Yok da bunun bir 10 tane falan var. Can Dündar 16
İlginç adam ya. Kel ilginç. Neyse.
Türkiye'de belgesel yapımcısı gıyabında mahkum yurt dışında. Ben değil mi öyle? Türkiye'nin yakınları.
Oh, something came to my mind.
Aynı şey var. Biz de aynı şekilde konuştukları için. Oha. Bizim böyle eğitim zorluğu var ya. Biliyor musun? Böyle yol yarısı böyle.
If size is less than this, return res because I'm going to store the beginnings of the sizes of the sizes of the allocated memory spaces in a stack which we had defined in this lecture.h file. Since it's by constant stores 1024 elements, we're going to have to limit the number of we're going to have to limit the number actually set a lower limit to the number of spaces that are allocatable for our purposes for from our function to 1024 so that we can at the worst case store all of these spaces inside of that array. These are just convenience, not convenience, to program the program faster because otherwise it would take longer and we don't have unlimited time. Okay, so we have to create the stack. And stack of spaces. Actually, let's. Oh my.
Yani, ilk böyle şu an çok başlayalım. Fazla benzer mi? Bilgisayar teknikleri kapattım. Hadi.
Hayırlı olsun abi.
Bu bir çok sıkıntı.
Linux tabii zaten. Linux tabii. I'm just making modifications so that multiple stacks can be given, and this is not constant. It's taking more complexity than I expected because I did not expect anything. Oh my, have I not started that? I'm regretting, but we have to do this. We have given our hopes and dreams into that path. Okay, now let's push. Let's push the size to stack of spaces. Okay, let's give this pointer value. Do we use anything? Yeah, we do. So we have to give the stack to that. And other than that, I think we are not. Oh, I think we're not doing anything wrong other than that. Okay. So let's move on. If the offers current stack pointer -1 address minus pointer, the amount of spaces in between equals that of the last space pushed into the stack. We know that it's the lastly allocated space, and we just deallocate that by size, by not size, but by last space, and return 0 because the operation was successful, so that we notified the caller of that function that the operation has exited successfully. And if not, we can just, actually, we don't have to put else here. We can just push the last space back in so that it is the order of the spaces stack is not stored. And again, I'm forgetting this. And there you go. We have a custom memory allocator that is able to do nothing, but is working. Okay. We're not going to be incorporating that into this program, but because it would further complicate things even more. Okay, there's no problem. Oh, let's skip that. Skip that. In order to modify a variable in some scope, but by a function, I would show you by implementing the function getFloat, which would take the string input from the user input as input and then convert it to a floating point number. But we don't have the time for that, so I will not be doing that. But instead, the thing we wanted to show with this was actually shown with this, that the variable stored inside of some things pointer is given to the function so that the function actually modifies the thing that is referred to by that pointer, so that you're able to modify things that are in the scope of a function by calling an outside function, which is pretty goodly exemplified here, that the stack variable passed on to this by the main function, the original one, is actually in the scope of the main, and we pass a copy of the pointer to that stack variable, which is inside of this main function. Let me scroll that down, which is actually over here, but let's presume that it's in the scope of the main function, and we pass its pointer to the push function over here. And since it has a local copy of the pointer, but since it has the right address to that variable where it's stored physically in the RAM, it is able to modify the content inside of the RAM in the address where this pointer, local copy of the pointer, points to. And since this address is the same as the one that is declared in the scope of the main, this actually modifies the variable which is in the scope of the main and used throughout the main by passing pointers as arguments to functions. This is a pretty good example of how you modify variables of some scope in a scope of other functions. It's a pretty good example, and you are definitely going to use that if you're programming in C. We have I++ and ++I operators. Let's read these in C from the internet. Sorry, as I talk longer and longer, my brain stops braining. And do we have that here? Do we have that? No, we don't. I guess we don't. Maybe we do. Okay. So as you can see, array a subscript, which is array indexing, is prioritarily higher than the prefix increment, which is this. So like this basically means that I'm doing this syntax in C. The C would first do the job with indexing the array with the variable e and take the value inside of the index I of this array and do the job whatever is required with that line with it, and then increment the value of the e, in contrast to our conventional use of this, which is a pretty cool concept that is able to shorten your codes a lot in various ways. We have multi-dimensional arrays as well, which is just the syntax. You have to specify the size of each dimension except for the first one, which is the first one is the one stated in this, and further you add arrays, further you add these brackets, and each one you have to specify its size, and they're all as well initialized to zeros. You may use this in more in like machine learning and other applications, but no one uses AI, C for AI, unfortunately, because programming world is not going to somewhere good. You can access the arrays elements by like this is the first array's second element. This represents that the multi-dimensional array syntax. And using pointers for different dimensions of arrays has to be thought with the same logic as said before. So interchanging arrays and pointers is the same logic as stated before. There's no difference in that. So let's talk about function pointers. Implement all of our functions for the stack as members of the stack structure. And let's remove this. And we said that. And let's talk about dynamic arrays by implementing our stack to be as long as the memory. We have a dynamic array. We're going to be talking about this so that we don't have the size limitation for our arrays inside our C programs, and then end the lecture. Function pointers, although one minute. Senin bilgisayara ne oldu?
Benim kelime kafamda açılmıyor.
Baksana elektrik geliyor mu gerçekten? Başka bir şey sok o prize. Prize başka bir şey tak. Elektrik geliyor mu diye bak.
Ne şey açıldı? Şu son bir ama şarkıdan yazdığı program vardı ya.
Hı.
O açıldı.
Şu an mı?
O açıldı. Böyle şey oldu. Kapalı.
O açıldı sonra kapandı mı? O açıldıysa bilgisayarda bir sorun yoktur. Muhtemelen Exxon 1'de bir bug vardır. DNF bir şey yapmıştır.
Şu an kapalı bilgisayar ama açıldı.
BIOS'a girebiliyor musun?
Rege karşı. Dersin bitti mi ya?
Yok, bitmedi. Neyse şu ders bitsin de bakalım, olur mu? A function pointer is a pointer that stores the address of a function, allowing functions to be passed as arguments and invoked dynamically. This basically means that you can behave to functions just like you do to pointers of variables. And this is a pretty cool concept because it enables you to pass functions as arguments to other functions, so that, like, for example, one function of your own has to choose according to a user input to use some function or other function, some algorithm or other algorithm inside a specific problem. And according to the user input, you can pass different functions implementing different algorithms for that problem, so that the invoker function would invoke one of them according to user input's choice. It is also, yeah, this is pretty much the most basic use case for a function pointer. It is just to, it is just a way of, let's say, int function invoker. Let's say we had a function called function. Instead of passing this as this, you're passing this as this, okay? Instead of passing to the function invoker function, the name of the function, you're just passing it to in the pointer syntax. There's no difference. There's difference. One of them is invalid, but this is the basic idea behind it. The same idea that you might expect once you gaze the first time to the concept. The declaration is as follows. I'm not going to be going further into that because it's not that important. You can always, as we've stated, always search for that for your own, and you are encouraged and are mandatory to do so. Function pointers as arguments, you can see the example here. I'm passing these swiftly because we can also define an array, because we're going to have to implementing, what is this ending guy doing here? We're going to have to be implementing new things over here. One of the cool things, you can also return function pointers, by the way, by using C's interesting syntax of, say, this function would return a function, and I don't know how it does that. So let's have a look at this. Maybe so. Maybe so. So no, it's like so. So like so. Okay. I don't know how does that. How do we do that? So return functions, function pointer in C. I'm not using this often in my programming. That's a pretty cool concept. Okay, so it is like this. Okay.
Ters varsayımda bu tutulmuş şeyi mi istiyorsun? Ben of culture.
Ama man of culture değil, direkt the man of the culture.
Where's the culture?
Bu culture. Let's search for that. We're in a lecture, guys. Some of us are trying to learn, okay? Functions as struct elements. if you have been programming in other programming languages, you might be familiar with the ridiculous concept of OOP, which is short for object-oriented programming, in which they define classes and define methods for these classes. They sort of like do the same thing as the struct does, but in a more complicated and unnecessarily easier way, because structs are not that hard. But they introduce some concepts as polymorphism, inheritance, abstraction, encapsulation, just to make things a little bit more complicated so that they can use more RAM. Actually, I'm not against Python's OOP, but many of the other languages just do it pretty bad. It is just think of it for right now as a advanced version of structs, and the one of the most fundamental differences you might realize in between them is that we have so far used, as you can see in that file, used variables as elements to a struct, but from now on we are going to be able to be using functions as elements to that struct as well. So that's one of the most basic things you might realize when you first look at the two side by side. But we're not going to be concerning ourselves with OOP, because even if C supports functions as elements of structs, it is not an object-oriented programming language. Object-oriented programming concept was not there when C arrived. C is pure in that sense, but it allows that, and it goes on to show that it is not that basic difference of having elements, having functions as elements, structs, is not the essential difference in between them. And let's have a look at that. This is the process of a programmer trying to figure out what to do. So you might be experiencing same things by yourself as well. Function pointers then explicitly passing this parameter. It says here that we have to define something like this. And okay. So we have to do we have it here? Let's use this one. Kafam çalışmayı durdurdum. We are going to have to include this here. Like, let's say the pop function. Okay. The pop function is going to, as you can see, turn an int, and let's see, and it's going to take the input stack and nothing more. I guess it's a valid syntax. Of course, it is. It's known. So let's say so, and let's see if we can access the elements inside of a structure with this thing. How do we do that? So it actually client actually it's able to take the argument of that. So maybe let's try this struct stack and try this. Okay, let's try this. All right, so this works. And let's type this back into stack so that we don't have to change everything. Maybe this. No, maybe this. Okay, we have to use struct again. Okay, this works. Now we have assigned and then the struct. We have been able to do this of our own. And let's come here and assign to that element the pop function, which is this syntax, I presume, is this syntax maybe? Okay, this works. Now let's test this out by, why does it not work? Sorry. Okay, now. And why does it not work? Why do we have too many arguments to exert single argument digit? I have two arguments. Why say so? Do we have another thing defined as push? Maybe this one. Solve the problem? No. We don't have anything. Oh, maybe this. Yeah, we have to change that. Actually, let's leave it open so that it does not give out any errors. Okay. As you remember from the previous lectures, that we are either going to, when declaring a function, before actually writing the code for it, maybe later after the main function or in some file that we're going to include after declaring it, we either can leave the arguments and the return side void, which means nothing, or we can give the whole thing. And if we give something that is not the same as the thing that is going to be declared afterwards, it's just going to throw out an error. And this approach is also unsafe because it can lead to compiler not checking whether the function is properly used throughout the program, but we're not going to be concerning ourselves with that for the moment. Okay, instead of using the pop function, which I believe we don't use. Okay, let's implement push as well, because I'm not going to concern myself with changing all of these pops into classes with taking the argument of struct stack pointer. I'm just gonna go on with the thing that is used independently of this file in the main function over here. So we're just gonna say, let's say this is stack, and let's say over here that this equals to push. Do the same thing with that as well. Okay, we forgot one thing. This. Why does it not work? Why does it not work? Oh, it does not return. We forgot about that. Okay, this has to be working right now. Okay, now let's come over here and stack push. Let's run this and see if we have achieved a primitive version of object-oriented programming, which we have certainly not, because as I said, they're completely different in their own regards. But hey, we're doing simplifications here. A.out maybe. And we have some errors. Conflicting types for push have void in stack, aka void. So what do we have different here? See any difference? Int digit stack pointer and cannot see any difference in between. Yeah, I'm doing something wrong. Let's change the name for that. Let's change the name for that. Let's change the name for that as well. Let's rerun this. So it's still giving an error. Conflicting types for push have void int stack, and we got int stack. So why does it? Maybe we have to just delete these. What? Okay, we have to just delete these maybe. Okay, this was the problem then. All right, now this works. The problem was that the definitions made here did not match these ones. You might ask, you told us that we could just write these and then this would be no problem. But because we did not include this after the main, this would give an error. So this was the case for that. Let's remove this. And let's talk about the dynamic arrays last and end the lecture here. As we've said, array sizes have to be specified when defining arrays in C. And we have a workaround for that. Actually, not a workaround, a thing that is provided completely by the language, and a thing that is pretty good to be used, because you may define an array of size, let's say 100,000, but it may run out. We have the program GCC written in C, which is able to take the Linux kernel and compile it down, which is millions of lines of code, which is when the GCC takes all of that into RAM, it has to load bytes and bytes of memory, and it's also compiling our code as well, which is only a few bytes. So it has to have an array that is able to meet the needs of both. And since it cannot know the maximum amount of code that is going to be fed to it, because there are servers around the world that is constantly feeding GCC with lots of things. ChatGPT is compiled in the OpenAI servers, and there they have millions of lines of code for that. They cannot. Don't tell to me that the thing is written in some other thing. All of the things always come down to C in some way. Okay. So we have to have some way of changing the space that our array occupies in the memory that the array has. Just like you have in Python, we call these dynamic arrays, and we want to have that not only for allocating more space when we need more, and also for not allocating more when we don't need it. Maybe deallocating them, maybe not like allocating just enough for our purposes at the beginning of the program. And that's what we're going to be looking at right now, which is the dynamic arrays in C. It is just a pretty standard practice, really. We are just going to copy and paste some code from here. And as you can see, we have used malloc and free functions from the very beginning. We're just going to use calloc and realloc right now, which I'm pretty excited to use because I haven't used them in my life. Okay, we are going to calloc. We are going to use the calloc to allocate enough space for our array. And since arrays are basically pointers and the calloc returns pointers, we are just going to, just like we do with malloc, just like we do with malloc, we are going to calloc that and acquire our pointer. So let's start with this calc. Maybe let's start with 1024 as always. And oh, wait, what did I do here? Okay. Okay. Sorry. What am I doing? Why did this switch sides? Whatever. Now, instead of fixing a fixed a instead of creating a fixed array, we have to, I guess, define a pointer. Let's see if this is the case by looking at the documentation for calc to see what it returns really. If it can be more quick, as you can see, it returns a void pointer, so we would have to cast that into our desired pointer as well. So in the beginning of this over here, we have to right now initialize our stack, calc our stack as well, just with the right amount of maybe init stack size, maybe, or maybe let's implement a function over here init stack, and it's going to take the value of the stack, and it's going to do all of these operations in here to make it more modular, because all of the operations are done over here, and we're coming here and just doing some work about this over here. So this is not ideal. Let's get that, and let's initialize its stack pointer to be not stack pointer, stack to be calc element size, which is the initial stack size, and then the size of char, because our type of array is char, and we have to cast that into a char pointer. And let's move this to here as well. And since we're passing the pointer as stack, as we've been talking about, we're modifying the actual stack. And even if it was not in the global scope here, we would have been able to do this. Call to undeclared library function. So where is the calc function is located? It's located in the stdlib. Okay, we have to include the stdlib age, and the problem is resolved, and just we need to define init stack size to be, let's say again, 1024, and under that init stack size. Okay, now what do we have the problem? Oh, okay, this is the init. Okay, now everything. Okay, the size of operator is also for the wrong thing. Okay, this is all good now. Now, let's from the now beginning create a function called check stack avail, which is going to check if available space, if there's available space in the stack, and if there's not, it's going to increment it so that we can still work around. We're going to implement this function in a minute, and we don't have to put this in these because they're already popping out two elements and pushing one. Definitely they're going to have the required space to push that last one into the stack. And let's add something so that if it's null pointer, maybe not error checks, because we don't have the required time. Check stack avail, and the function is going to take the input of a stack pointer, and then how much it increase. It has to increase that, of course, by bytes. So we have to take the number of bytes each element occupies, bytes by elements. And this size t is the standard data type to be used to express the bytes occupied by a data type. So keep that in mind as well. So let's define stand inc as well, which is short for standard increase. Maybe it is 150 point 112. Undef that at the end as well. And let's work around this. But before, let's do this size of int because we have to. And then let's come over here. If stack pointer, and we have to define the size of the stack as well. And let's init that to init stack size so that we can keep track of the size of the stack and then compare the stack pointer with that size to get an idea of whether the stack is full or not. And let's see if this is the case. It's going to first increment the size of the stack by the number of by inc size. Actually, it's going to do that after reallocating, so that we are making sure that we first allocate the required space and then we notify the program of that. I think we do this. Okay. So we stack is now equal to realloc, which is the stack, just writing these from these, and we have to specify the new size. So let's actually do this so that we are making it more convenient. Stack size multiplied by size of, do this parentheses, just not to confuse ourselves with the precedence. I don't know about the precedence in C. You can just always check it out by yourself, and by size of int. And we have to be done. Okay, this has to be it about implementing a dynamic array for our stack over here. You can see that it terminates by cc lecture c, and then a dot out 2 and plus segmentation fault we have. Why do we have a segmentation fault? That means, of course, we are accessing somewhere we mustn't be accessing. And let's change this bullshit. I just don't want to concern myself with that. Okay, is it working now? Maybe this was the problem because it wasn't the problem, of course, because there's no problem with that code. We have problems with something else. And I don't know what is. I don't really know what is. Or we have to paste that to this as well. Let's see. We're definitely accessing somewhere we mustn't be accessing. Oh, because we haven't called that init stack function at the beginning. So sorry about that mistake. We have to init our stack. So, and okay, now it's working, as you can see. So this is the final stage. Our reverse Polish calculator is. It's a pretty interesting program, to be honest. It does a lot of things, and it is not able to do many more things. It has been very helpful to us in showing many things about C programming, in teaching us that. So I'm thankful for the reverse bullshit notation. Why am I using bullshit so much today? And just ignore that. That is the end of today's lecture. Thank you for coming and listening. Don't forget to practice. And this standard talk finishes right over here, and goodbye.